This video is going to introduce two new gates, which we did cover in the Basics of Electrical Engineering playlist. The link will be in the description. But we're going to return to the NAND and the NOR gates. And to do that, we're going to need to recall our AND gate, where the function is given by A times B, and we have the following truth table. Now, we can create a NAND gate simply by adding an inverter onto the output of the AND gate, such that the output of the original AND gate becomes flipped, and our new truth table looks like this for the NAND gate. And if we take the function of the NAND gate, which is the inverse of the AND gate, and apply De Morgan's law, we can expand that function as A bar plus B bar, which you can see by the plus sign, we have an OR gate. So what we can say is that the NAND gate can also be represented as an OR gate. So this may appear a little bit confusing why we're doing this, because it looks like we've increased our complexity. But we'll get to the reasoning for that in this first example. And for that, we want to look at a function given by AB plus CD, and we want to express that as a combination of NAND gates. So if we take that original function and just map it into the corresponding combination of logic gates, we have two AND gates, one for A and B, one for C and D, and those are summed together with an OR gate. And what we're going to do is expand that simply by adding inverters on the output of each of these AND gates and then having a secondary inverter, such that if we call this first output F1, we would have F1 here. After this inverter, we would have F1, the inverse of that, and then after this inverter, we would have F1 again. So now what we can do is draw a dotted box around these two inverters and the OR gate, and we know that that will turn into a NAND gate. And we also know that having an inverter on the output of an AND gate also can be simplified by a NAND gate. So what that does is it allows us to collapse this circuit to this circuit. Again, why do we care about this? We have three gates here, we have three gates here. And it appears we really didn't do anything useful. But that's when we need to ask ourselves, what are these logic gates? Because right now they just seem like these magical devices that can output something given their input. But inside of all the different logic gates is a unique combination of transistors. And transistors are what we covered in the Basics of Electrical Engineering course, but we don't need to dive into the internals of these logic gates for the scope of this course. What you want to take away is that NAND gates have 4 transistors, and your OR gates or AND gates are comprised of 6 transistors. So if we look at the amount of components in our original expression and what we simplified it to for the NAND gates, we would have 18 transistors that make up this circuit, and we would have 12 transistors that make up this circuit. And again, what we want to do is optimize as engineers. So now we can look at the next kind of gate, which is a NOR gate. And we know the function of the OR gate is simply A plus B, and we have the corresponding truth table. Now if we add an inverter onto the output of the OR gate, we end up with a NOR gate. And the NOR gate is simply the inverse of the OR gate. So the truth table is as follows. And the function to describe the NOR gate is given by A plus B with the inverse bar over it, which again, using De Morgan's law, we can simplify as A bar times B bar. So now we can set this equivalent to this to arrive at the following. And this allows us to make circuits in terms of NOR gates. So to look at an example, we want to express this function where we have in parentheses AB plus C and that whole term multiplied by D. So a 4-input system, we want to represent that as a combination of NOR gates. So expressing this function, we can simply have this circuit on the left where we have that AND gate for the input D. We have the OR gate, which is combining the outputs of A and B through an AND gate with the input of C. Again, we're going to play the same trick of adding a bunch of inverters such that we have this circuit here on the right, And we can draw some dotted boxes around the components that can easily convert to NOR gates. So what we end up with is a circuit that looks like this, where we have 3 NOR gates, but we also have these 3 inverters. So given these inverters, we can do a trick to see how we can represent those as NOR gates as well. So we're going to take a NOR gate, given by X and Y as the inputs and F is the output, and we're going to have a truth table. And now what we're going to do is get rid of Y and simply call that X. And from the truth table, we now have 2 inputs, X and X, and we can't physically have the combinations where 0, 1 and 1, 0 even exist. Now for redundancy, we can get rid of that second X and tie the inputs together. And we can compress this truth table simply as 1 input, 1 output, 0 and 1. And what we're left with is a 1 and a 0. So what this says is that this NOR gate is equivalent to this inverter. So you could adjust these inverters to NOR gates.